Welcome to Dr. Jimmy's Applied Calculus, ready for section 3.4. We're going to look at limits again, but move to some discontinuities. Okay, up to this point, mostly we could do limits at continuities, where we could substitute a value into an expression and get a number. So we're going to concentrate on what are called rational functions. So a rational expression is an expression made up of a polynomial divided by a polynomial. An example of such a creature would be something like 3x squared plus 2x minus 6 divided by x squared plus 6x plus 8. So a rational expression, the ratio of two nice things, in this case polynomials. So any two polynomials divided is what we call a rational expression. So if we look at limits for such a rational expression, we could attempt to look at this in a continuous fashion. So, will the value of the function coincide with the limit? So, we substitute the value we're approaching, in this case 0, into the expression. In this case, it comes down to minus 3/4. So we get a nice limit. So continuous, if we graph the curve y equal this expression, we would have the curve go right through a point at height minus 3/4, no problem. Okay. So again, rational expressions, polynomial, devised with this property of continuity. But not everything turns out continuous everywhere. So if we try the limit approaching minus 2, 3x squared plus 2x minus 6 over x squared plus 6x plus 8. And then attempt substitution. So 3 minus 2 squared plus 2 times minus 2 minus 6 all over minus 2 squared plus 6 times minus 2 plus 8. So we get 2 in the numerator and 0 in the denominator. So now we have a problem. Okay. We have division by 0, so we don't get a value. So actually the expression is not defined as a number at x equal minus 2. So we get a discontinuity at x equal minus 2. That is, in this case, because the function does not have a value there. But it may still have a limit. Now we looked at the conceptual division by 0. It said if we could determine the things close to 0 to be negative, then the 1 over 0 would be minus infinity, and 2 of those is still minus infinity. If we could determine the values of things near 0 to be just positive, then the reciprocal of 0 would have been a plus infinity, or 2 of those being infinity. So, although we don't get a number as the possible limit, we might still get a conceptual limit of infinity or minus infinity. Okay. And so this is the case of a non-constant divided by 0 in our evaluation. So we'll have to study this a little further. And so what's true of rational expressions is that if we look at the right and left limits, they will come up as either a division by a 0 plus or a 0 minus. Okay. So, if we look at the right limit, we're going to look at x bigger than the value minus 2. So we're going to take a value close to minus 2. We know we can't evaluate at minus 2, but let's get very close and evaluate there instead. So something like minus 1.99. Okay. Almost minus 2, but just slightly bigger. So let's look at this denominator. And take our test value, minus 1.99. So denominator is x squared plus 6x plus 8. So that's a positive number, not too big, but it's still positive. And that tells us that if we look at the limit from the right, we get the 2 over 0 evaluation. But the things close to 0 are actually positive. And so we don't get a number as the limit, but we do get an infinite limit. So So we might say as x gets close to minus 2, we find the values of the expression growing without bound instead of going close to a number. In this case, we should say gets close to minus 2, but remain bigger than minus 2. So we do get a limit on the right side, although not a number, but infinity, or an infinite limit. Then we could look at the left-hand limit. With this same expression. And so now we need x to be less than minus 2 as we approach minus 2. So let's pick x equal minus 2.01. Very close to minus 2, but not quite. And also less than minus 2. And so we'll look at the denominator again and test this value. So x squared with a minus 2.01, 6x replaced by minus 2.01 plus 8. And now the computation gives me 0.0199. And so negative. So if I look on the limit approaching minus 2 but stay to the left side, I get evaluation of 2 over 0, but now I know that the things close to 0 are actually negative, and so these things grow without bound as we get closer and closer to minus 2 on the left, but we get 2 minus infinities, or negative infinity. So we have a left and a right limit, although not numbers, are conceptual very, very large, or infinities. Now, if we look at the limit as x approaches minus 2, trying to come from left and right, we have a problem because it's trying to be very large positive on one side, very large negative on the other side. So we can't put those together. So left and right limits are not the same, so we don't get a limit. If they happen to be the same infinity, either a plus or a minus, then that would also be the limit. Now, what we just looked at, if we look at the graph of y equal this rational expression, 3x squared plus 2x minus 6 divided by x squared plus 6x plus 8. Now, let's take a piece of this graph, what we just looked at, the limit as we approach minus 2. What does this say about the graph? Well, what we found was the limit if we approach on the right was infinity. So that means that the heights here become infinitely large or grow without bound. If we approached from the left, we found the limit to be minus infinity, and so it grows without bound but negative. So that kind of characteristic at x equal minus 2. And so in this setting we see these graphs approaching this vertical line x equal minus 2. So maybe away from minus 2, the rest of this graph I haven't put in, but near minus 2, this is our picture of the graph. So it has this asymptotic behavior. As we get closer, it looks more and more like this straight line. So up in here and down here. So, but that's a vertical line, so we would call that a vertical asymptote. So vertical asymptote, we would have the limit at the value being infinite, either on the left or the right, or in this case, we get a minus infinity and a plus infinity on both sides. So that gives us a vertical asymptote. Now let's take a rational expression. Three x squared plus 7x plus 2 and divide by x squared plus 6x plus 8. So I changed the rational expression again. Let's consider this limit as x approaches minus 2. If we attempt evaluation, we find a continuity or discontinuity at the value x equal minus 2 again. Okay. This one's a little different. This one comes out to 0 divided by 0, which is an indeterminate form of division by zeros or infinities. So if it was non-constant by 0, we had a way to look at it. Essentially, it's an infinity, the reciprocal of zeros being infinities. we had to worry about the sign. Here, though, we get 0 over 0. So it's not going to work the same. It's an indeterminate form. We're going to have to look at the limit at this discontinuity in a different way. So, but when we evaluated, what we did find is that if we plugged in x equal minus 2 into the expression for the numerator, 3x squared plus 7x plus 2. Oh, we got 0. So x equal minus 2 was a root of that particular polynomial. But that means x minus a minus 2, or x plus 2, is a factor. Okay, so the fact that we evaluated and got 0 in the numerator said that, oh, x plus 2 is a factor of whatever that polynomial is. So now, 0 over 0 case, we're going to look at dividing out this factor, this x plus 2. So we could do that in different ways. Okay. We could attempt to factor and cancel the common factor. We could do long division. In this case, for an illustration, I'm going to do synthetic division. So I have the root of minus 2. I have the coefficients 3, 7, and 2 for this numerator polynomial. So run this through. 3 plus 0 is 3. Multiply minus 2. Get minus 6, add, I get 1, multiply, add, I get 0. So, synthetic division, though, gives me what's left once I factor. It should be 3x plus 1. So, one way to divide, just use synthetic division, and so I get what's left after I factor out x plus 2. But the same is true of what I found for the denominator. X squared plus 6x plus 8 also evaluated to 0. So I get the same consequence. X equal minus 2 is a root. X plus 2 is a factor. So I'm going to divide it out again. So I could use synthetic division, other methods. I think in this one it's a fairly straightforward factorization. And I know what one of the factors has to be x plus 2, so that leaves the fact that the other one would be x plus 4. And so once I get common factors, I end up at x plus 4. So different ways we might get there. But we know what the factor is, so I can either do division in a more long division way, or I know what to factor out. So I factored out the same thing from numerator and denominator. So where I started with the expression x approaching minus 2, 3x squared plus 7x plus 2, which was divided by x squared plus 6x plus 8. I knew what to factor out or divide in each case and have reduced it to the result of those divisions. So for the numerator, I ended up at 3x plus 1. In the denominator, x plus 4. So, except at the value minus 2, the expressions I'm looking at are equivalent. And so, once I do this reduction, I can attempt to evaluate again, which in this case yields minus 5 over 2. And so that would be my limit. So this was the case I started with 0 over 0, which told me that x plus 2 is a common factor, numerator and denominator. And so I simply divided it out of both. And we have different methods for that. So now we don't have asymptotic behavior. We just have a place in the graph that should have been minus 5 over 2, but we couldn't define it there. So graphically it would approach minus 2, it would just have a hole and then go on, instead of asymptotic infinity behavior. I suppose it would look a little better if I made at least made the hole at minus 2 to be negative instead of positive. So, limit as x approaches some value of a polynomial expression divided by a polynomial you get 3 possible cases. A number, non-zero over 0, or 0 over 0. So, and we address each of those differently. If it's a number, that's the limit. If it's non-zero over 0, left and right will be infinities. And then we have to determine plus or minus. If they're the same, then we get a limit. If the left and right limits differ, then we don't get a limit. 0 over 0, different method. We determine that x minus b is a factor and divide it from the numerator, divide it from the denominator, and then try again, which will bring us back to one of these 3 cases. And so we may finish, or we may have to do that division more than once.